Hello and welcome to another session in physics. In this session, we'll be looking at the topic refraction of light. Refraction of light. But before that, let us review the previous lesson. Welcome back. Now, in our previous classes, we've been talking about reflection, and we said reflection is the ability of light to bounce back off a surface. Now, it might interest you to know that light is a wave. Light is a wave known as light waves. And as it is with every other wave, all of these waves have characteristics. Some characteristics of waves such as light include reflection, we have refraction, we also have things like polarization, we have diffraction, and we also have interference. These are a few of the many characteristics that light waves possess. So our focus today is on refraction. Now, what is refraction? Refraction occurs when there is a change in the direction and the speed of a ray of light when it passes through from one medium to another medium of different density. When there is a change in the direction and the speed of a ray of light as it passes through from one medium to another medium of different density. For example, let's say as light passes from water to air, or from air to water, anyhow, from air to water or water to air, light will change its direction due to the density of the medium it is passing through. And that is the phenomena that occurs when you put a spoon in a bowl or a plate filled with water, for instance, and then you look at this spoon from outside. It's as if this spoon is bent. Like, for instance, here, and then it looks like this. It's as if the spoon is bent. But in reality, the spoon is not bent. It is just the principle of refraction coming to play. Yes, the phenomena of refraction is happening, which makes it look like that object in water is bent, when in reality, it is the light that has bent. Remember, light is what helps us to see objects, and if light passing through an object or through a medium is its velocity has changed or its direction has changed, then definitely that object we're looking at will appear to be changed as well. So like I was trying to say, when a ray of light travels from an object that is optically less dense, such as air, to an object that is more dense, such as water or glass, that particular ray of light tends to bend. Also, a ray of light passing from glass to water, this time from a more dense medium to a less dense medium, or from water to air, and the density continues to reduce, the ray of light is bent away from the normal, which makes the ray of light look much more straighter. Now, when a wave or a light wave is refracted, there are about four things that happen. The first thing that happens is that its direction of travel changes, its velocity changes, its wavelength changes, but the frequency remains the same. Now, this is an example of a rectangular glass block. This is a rectangular glass block, and inside this rectangular glass block, we have an incident ray of light focused on it, and then we have the emergent ray. The emergent ray is coming out as a result of the incident. But notice that it is not straight. It is not a straight line like at this angle and then very straight. No, it's not. The reason why it is not straight is because the light has been refracted as a result of passing through air and entering into glass and then out of glass again. So this angle that the incident ray makes with the normal is what we call the angle of incidence, and the angle that the refracted ray makes with the normal is also the angle of refraction, denoted as I and R respectively. Now let's look at refraction through rectangular prism. For us to understand that, we need to get ourselves in terms with two laws of refraction. Remember, reflection also has two laws. Now, refraction has its two laws. The first law of refraction says that the incident and refracted ray are in opposite sides of the normal as the point of incidence, and that all three of them, the incident, the refracted, and the normal, are all on the same plane. The second law of refraction is what we know as Snell's law of refraction. Snell's law of refraction states that the ratio of the sine of the angle of incidence to the sine of the angle of refraction is a constant for a given pair of media. That is Snell's law of refraction. And most times you will encounter it when you do your practical physics and you have to do a rectangular glass block experiment. The constant, which is n, is known as the refractive index. Written like this is the refractive index of the second medium with respect to the first medium. Second medium with respect to the first medium. It is a number which gives a measure of refraction or bending of light as it travels from one medium to another. At this point, let's also look at what we mean by the sine of the angle of incidence and sine of the angle of refraction. When we have something like ANG as we have here, it refers to the angle of incidence. Its sine in air, and we have GNA here, it means sine of the angle of refraction in glass. Sine of the angle of incidence in air and sine of the angle of refraction in glass. Now we have what we call the principle of reversibility of light. The principle of reversibility of light states that the ANG, which is the sine of the angle of incidence in air, is equal to the inverse of the sine of the angle of refraction in glass. Furthermore, we have that the speed of light in glass is over the speed of light in air, also gives us the principle of reversibility of light. Now this is a diagram of the refraction through triangular prism. We have a rectangular prism, also known as rectangular glass block, and then we have triangular prism as well. So this is what an experiment, a typical experiment of a triangular prism would look like. Now one thing we have to point out here is that the angle between the incident ray, as you can see from the diagram here, and the emergent ray is known as the angle of deviation. The angle between the incident ray and the emergent ray is known as the angle of deviation. The angle of deviation decreases or reduces as the angle of incidence increases. And this is the equation we use to find the refractive index, which is written as n sine. We have a over 2 plus d over 2 plus then all around sine a over 2. So this is the formula we use to find the refractive index. Now this is what we mean by total internal reflection. Total internal reflection seeks to help us understand what happens between the refracted ray, critical angle, and the angle of incidence. The three relationships together is what we have here. So for the first one, the angle of incidence is less than the critical angle. The ray is refracted with a very small reflection. For the second one, the angle of incidence is equal to the critical angle and ray emerges along the edge of the block. For the third one, the angle of incidence is greater than the critical angle and the ray is totally internally reflected. Now look at this slide here. You will notice what happens when light passes through a very small angle of incidence from a denser medium, or we say a thicker medium, and it goes to a less dense medium. So for example, from glass to air, of course we know that glass is more dense than air, or we say from glass to water, both of them do not have the same density. So when light travels from a denser to a less dense medium, say from glass to air, the refracted ray that is being produced is very, very strong. But when the reverse is the case, we say that the refracted ray is very weak. Now, when the angle of incidence increases, the angle of refraction also increases. So we say the angle of incidence is directly proportional to the angle of refraction. At a certain increase of the angle of incidence, the angle of refraction gives us 90 degrees, which is a right angle. This angle of 90 degrees, the angle of incidence in the denser medium, for which the angle of refraction in the less dense medium is 90 degrees, is referred to as what we call the critical angle. It is at this point that the ray is said to experience what we call total internal reflection. An example of total internal reflection is mirage on the road. I don't know if you've been able to engage in a long distance journey, and as you are moving on the road, you tend to look far ahead on a hot sunny day, and it's as if a body of water is lying on the road there. But as you get closer, you discover that there is no body of water, but it is simply a phenomenon that happens when the refractive density of warm air is less than that of cool air, and light meets a layer at a critical angle and it suffers total internal reflection, giving birth to what we call mirage. In English, we say mirage refers to an apparition, something that is not real, a kind of a makeshift phenomenon that will happen where we think something is happening, but that thing isn't actually happening, or it doesn't actually exist. So that is what we mean by mirage. Now let's talk about real and apparent depth. When we think of a thick slab of glass that appears to be only 2/3 of its real thickness when it is viewed vertically from above. Another thing is when water in a pond appears to be only 3/4 of its real depth. If you've been to a swimming pool before and you look at that swimming pool from on top, it seems to you like that swimming pool is not as deep as it looks until you put your leg inside. When you now put your leg, you discover that what you were looking at is actually what we call apparent depth. That is not the real depth of the swimming pool. So we have real and we have apparent depth. Both of them are not the same. So refractive index is given as real depth over apparent depth. Real depth is the actual depth of the material. Real depth is the actual depth of the material, where if that material is 5 meters deep, it is 5 meters deep really. But apparent depth is how it appears to the eye as a result of refraction of light traveling from a less dense medium, which is air, to a more dense medium, which is water. Now this is refraction through lenses. When we talk about lenses, we talk about glasses that are used as magnifying glasses. We see examples of these in microscopes, we see it in telescopes, we see it in cameras, and we see it in projectors. The human eye has a natural lens which enables people to see very clearly. We have two types of lenses, which are converging lens and diverging lens. Converging lens brings light rays together. Remember, I told you converge means to bring together, while diverging lens spreads light rays apart. It spreads light rays apart. Converging lens or convex lens bulges at the center, while diverging lens or concave lens gets thinner at the center. So this is a diagrammatical representation of lenses respectively. This is a diagrammatical representation of lenses and where objects, where they are placed, what they will look like according to the material of the lens. Now, for a converging lens, when you want to produce the image of an object by a converging lens, we have two major rays that are required. We have a ray that has to go from the top of the object to through the lens, and from the middle, which is the center of curvature. When it passes through the lens, it has to pass undeviated. That is the first major ray. Then we have the second ray that has to pass from the top of the object through the principal focus, which is F. At this point, where the two rays will interact or intersect with each other, we say the image is formed. Now let's talk about a simple magnifying glass or a simple microscope. A microscope, put simply, is a glass that helps us to see objects more bigger than they really are. We use it in reading and studying biological specimens. On the other hand, the complex lens gives us an enlarged upright virtual image of an object, because this object is placed inside the principal focus. A complex lens is the principle that is used in the construction or manufacturing of a microscope. That's it for this topic. Thank you for joining us in this lesson. To refresh your memory on what we've just discussed, please take the test that will appear on your screen.